So let's switch back to the slides. This is repeating what this is repeating what I defined just now. So basically, OPTJ is a new function we defined. This basically consists ask you to solve a subproblem, problem that only consists of jobs of 1 to j, right? So the in English is max weight of any subset of mutually compatible jobs for the subproblem, right? So we are looking into the subproblem that consists only job 1 to j, right? Right. So at the end, we want to be able to solve the entire problem, right? I give you all n jobs. Can you find me the optimum problem, right? So in terms of this function, right, expressed in terms of this function, basically, we just want to compute the OPTN, which is the max weight of any subset of mutually compatible jobs, right? Right. So basically now what we saw that the next thing we want to do is really to build up a recursive solution, right? A recursive solution for the OPTN I, right? So OPTI basically means that you are given I jobs, right? I don't know what it looks like, but there are a total number of I jobs, right? And not only that, I also know that the finishing time Fi is largest, right? Fi is largest is really just by definition, right? Right. So we sort of want to solve this problem, right? This is what the OPTI is about, right? And our recursive basically utilize this crucial observation, right? There can only be two cases if I look at the two jobs, right? So there are only two cases. The case one is that the job, the i's job is not used, not included in the optimum solution in the optimum solution in OPT solution, right? In this case, basically, we sort of know that the optimal solution would look like the OPT I minus one, right? So basically, I decided to not use the ice item, ice job. Then basically I really just want to try again and see if I want to find the optimal solution for the first I minus one's job. What's the optimal solution for that, right? If I know that, and I on top of that, I also know that the i's job is not part of the optimal solution, then this one would be the optimal solution, right? Similarly, this case two basically means that the i's job is included, right? In this case, basically, that sort of means that anything that's compatible with the ice drop must not be able to, cannot appear in this final solution, right? So basically, what we need to solve is that really just that we don't need to figure out the how can we want to solve the subproblem that's starting from the first job to PI's job, right? So let me switch back to the whiteboard and explain this idea again, like in just reiterate this very important idea. The very important idea looks it's this one, right? So I have a lot of jobs, right? Right. So that's sorted that's sorted by the ending point, ending time, right? So now I have how many jobs? 1, 2, 3, 4, 5, 6, right? So let's say that I want to solve the LPT6, right? So the semantic, the meaning is that what's the optimal solution if I want to choose job from 1 up to 6, right? Right. So I only have two cases, right? The case 1 is job 6 is not included, right? If job 6 is not included, if I know it's case 1, then OPT 6 would be the same as OPT 5, right? Because I know the jobs would not be included, right? So if I find the optimal solution for the first 5 jobs, together with the fact that 6th job is not included, then whatever optimal solution for the first 5 jobs would be the optimal solution for the 6th job, right? The case 2 is a bit that was a bit harder to explain just now, right? Job 6 is included, right? Right. So let's just examine what happens if job 6 is included. When it is included, right? So basically that means that this job 6 is included, right? So anyone that's not compatible with job 6 has to be excluded, right? Any job not compatible with 6 will not appear in the final solution. Right. So the numbers 3, so for this specific example, number 3, number 4, number 5 are not compatible with 6, right? They cannot, none of them can appear in the final solution. I just assume that number 2 and number 6 are compatible, right? So then basically you sort of need to find an optimal solution so basically you need to find the optimum solution for the first 2 and plus your last your sixth drop, right? Let me just repeat, right? So long as you decided to include this particular job over here, right? Then basically you decided to exclude, let me just use the black one. You decided to exclude everyone here, right? So if I just erase them literally, right? So basically you decided, so we sort of know that 6 is included, and we don't know the solution for this, the optimum solution for this period, right? But this period is exactly a subproblem, right? So the optimum solution for this region, for this region is exactly by definition. We just need to solve another problem, optimum solution of 2, right? The first 2 subset, right? So basically, in case 2 is correct, then basically let's say that the optimum, what we get is the optimum solution of the first 2 jobs, and plus your reward of the 6th job, right? This is, let's call the reward for the 6th job, right? So these are the 2 cases, right? So it's running over 1 page. Let me just cut this out. Can I? No. Can I cut this out? Yes, I cut this out. I move up. Never mind. Right? Actually, that's good enough, right? So basically, I do have 2 cases, case 1 and case 2. In case 1 is optimum 6. It goes to optimum 5, right? And in case 2, then it's optimum 2 plus R6, right? So one of these cases has to hold, right? So I only have 2 options. I either include the job 6, which means that optimum 6 equal to optimum 5, or I don't include the job 6, right? Which means that I first need to find the optimum 2, and then I'm going to collect the reward for the 6th job, right? One of them has to be right. So that basically means that by definition, my optimum 6 equal to the max of optimum 5 plus and optimum 2 plus R6, right? One of these 2 cases would be correct, right? This is case 1, case 2, right? So one of them is correct, and which one is correct? Basically, you just compute each of them and see which one gives you a better reward, right? So let me just write that more clearly, right? So this optimum 6 equal to max of optimum 5 and optimum, what is optimum 2, right? It's really just P of 6, right? Plus R6, right? P of 6, what is P of 6? P of 6 basically is there was a definition that's introduced in the slides, right? The largest index that's compatible with 6. Compatible with 6. Right. So here, right, so it's really just 2 cases, right? This is case of not including job 6, and then this is the case of including job 6, right? Job 6, right? Job 6. Right. So one of these cases, it has to be either include or not include, right? I'm able to compute the optimum solution for both cases. One of the cases has to be optimum. So if I take the max, right, I get the optimum 6. Right. This is the high level idea, right? So essentially, we are really just coming up with a recursive solution. This is optimum 5. This is optimum P6, which is equal to 2 plus this R6, right? So now so in terms of the computability, we at least managed to reduce the problem into recursive problem, right? Every time you recurse, you solve a smaller problem. So eventually, this algorithm will terminate, right? So, but the high level idea or message is here, right? If we just run the plain vanilla version of the recursive solution, it will take very, very long, right? So that's the reason we introduced one more layer of the so-called the memorization trick. And as you can see, if you don't use the memorization trick, the same sort of computation is going to happen again and again and again, right? So that's going to waste a lot of computation resource. And then as soon as you deploy this trick, a lot of problem all of a sudden becomes very efficiently solvable. Right. Let's just look at the Bellman equation over here, right? So that's exactly what we mentioned just now, right? So there's an obvious base case where j equal to 0, but if it's not the base case, right, there's two cases. One of them has to hold, right? Either you include the j's job in your optimal solution, or if you don't include, right? So we just wrote this as r, right? So it actually is w, right? There's some notation change, right? Pj basically, as the definition, is really just the job the maximum index that's compatible with j, right? So where's the definition, right? So it's over here. That's the definition of pj in case you are interested in seeing the precise definition, right? So now, the interesting thing is here is that as soon as you are able to write this down as a recursive form, you can immediately translate that really just into the pseudocode, right? This is the recursive form. Let me just, I'm not able to copy and paste, right? So this is the recursive. Let's see whether I can do the copy and paste here, right? So copy and paste image, right? So if I just look at the recursive form here, right? So my point is that if you have the recursive form over here, then when it's translated into the code, right, it's really very funny, right? It's almost the same, right? If j equal to 0, return 0, otherwise return this maximum, the whole crap over here, right? So you can essentially see that the recursive form over here, it's effectively a piece of code, right? In case you don't worry about the efficiency, right? So this code will be correct and will terminate, right? The only problem is that it's not efficient, right? It's so basically that there's a philosophical question here, right? In our course, our definition of algorithm is that we implicitly mean that we care only about algorithms that runs in polynomial time, or in other words, we care only about efficient algorithm, right? So this algorithm, as we can see, it's going to be an exponential running time algorithm. It will give you the correct answer, right? In terms of the output, it will be correct, but in terms of like this assessing whether this is in acceptable quality under the criteria set up by this course, this is not an acceptable algorithm, right? This, we would say that this is an incorrect, right? It's not that it's not going to the algorithm output something that doesn't make sense. It's really just that it doesn't meet our criteria that an algorithm has to be efficient. It's not an efficient algorithm. So if you I'll ask you to solve a weighted interval scheduling problem, you give me this solution, it's incorrect, right? So let me also explain to you why this algorithm is going to be running in exponential time, right? So the observation here is that the recursive algorithm is spectacularly slow because of the overlapping subproblem, exponential time algorithm, right? So let's just look into this problem, right? So I want to be able to solve the OPT5, right? Basically, that means that I want to find an optimum solution for the jobs, right? 1 out of 5, right? So what do I do here, right? So basically I want to find out optimum of OPT4, right? OPT4 plus OPT4 plus not plus and comma and OPT3 and weighted 5, right? So basically if I look into the specific structure over here, right, it's arranged in a very specific way, right? Any two consecutive jobs overlaps, right? So, but if I look at only jobs that are skipping, that are not consecutive, if I look at the first and third job, right, they are compatible, right? Compatible, right? Right. So this has a very, very specific configuration. So if I look at the fifth jobs, I want to find its optimum solution. I recurse, right? There are only two cases. The first case is I include job 5, not include, I think this case is not include the job 5. Job 5. In this case, the optimum solution would be job 4, right? The second case would be the include job 5, right? Include the job 5, right? In this case, right, so I collect my reward for job 5, and then I sort of find of the P of 5, which is 3, right? P of 5 is really just the largest index that's compatible with 5, right? The number 1, 2, 3 are all compatible with the fifth one, so the P of 5 is 3, right? This is optimum 3, right? And optimum 4, how can I solve this, right? So OPT 4, I continue to recurse, I make a max of OPT 5, OPT 3, right? And also the OPT 2 plus weight of 4, right? So this is all, again, the definition of the OPT 4, right? You can sort of see that we can continue to recurse. I have to solve OPT 3 and OPT 2, right? And similarly, I have to solve OPT 3 here and recurse and then max and then two terms here, right? So I can so you can sort of see the recursive tree that we are sort of constructing here, right? So this slide is actually making the recursive tree explicit, right? I need to solve the node 5 here is that just correspond to the fact that I want to solve OPT 5, right? So in order to solve OPT 5, I need the OPT 4 and OPT 3. And in order to solve OPT 4, then I need OPT 3 and OPT 2, right? This is OPT 3, right? And then this is OPT 2, right? Op2, Op3, right? Depending on whether you want to pronounce that as OPT or an Op, right? So, and in order to solve Op3, then Op2 and Op1, Op2 like breaks down to the basic case that doesn't need a recursive anymore, right? So this is the entire recursion tree. Like, what can we observe here? Right, so let's just erase out the what I'm drawing here, right? I just want to see the observation here. Our crucial observation, most crucial observation here is that if I look at the compute tree over here, right? This is opt3, right? So I'm going to compute optimum 3, right? If I look at the compute tree over here again, this is opt3 again, right? So it's sort of like when I recurse in solving the fourth problem, the OPT 4, I have to solve the problem of opt3. And then sort of after I get the result for op4, that I sort of forgot what I solved just now, and I need to solve the op3 again, right? So these two of the same computation happened twice. That's the very, very crucial observation here. Computation happened twice. So the whole idea of the dynamic programming is really just that if we sort of see the same computation appear again and again, can we just cache the result, right? So not only that, if you look at here, right? So this is solving the op2, right? Op2. And then this is actually also solving the op2, right? So it's not really just an isolated or insulated instance that the incidence that some of the computation is repeated, right? So this phenomenon is actually appears everywhere, right? So a lot of the computation are repeated. The op2 is solved twice, and then actually the op2 is solved 3 times, right? So and op3 is solved 2 times, and so on and so forth, right? So there are a lot of redundant computation, and our question is that can we avoid doing this kind of silly things or just repeating the computation, exactly the same computation again and then again and then again. So now let's switch to the whiteboard and then get to the very, very center of this dynamic programming, right? There's only one center and quite silly idea, right? So we saw that the same amount of computation happened many, many times, and then our goal is to be able to avoid that, right? In order to avoid that, right, the only thing we need to do is to introduce the idea of caching, right? So I create an array, right? So basically this array has 5 elements, 1, 2, 3, 4, 5, right? These are 5 elements, right? I initialize the array to be all empty, right? So, and basically intuitively, right, I have two cases, right? If it's empty, if if I don't know, if I never come, I don't know the solution, I don't know the solution, the opt I, right? Or basically equal to opt I, like otherwise, right? So basically that really just means that now we have this algorithm over here, right? So our recursive start with the 5th node and recurs to the 4, recurs to the 3rd, 2, 1, right? So this is how the recursive works, right? So basically when I want to, there are also other things that are waiting to be expanded, but when I want to compute the opt5, it's really equal to opt4, right? Max of opt4 and opt3 plus W5, right? So I'm basically executing this tree, right? I need to first find solution here, right? I before I find solution here, so my branching of the other way hasn't been expanded, right? So I'm only expanding along expanding the recursive tree along one direction, right? So when I want to solve the fourth node, right? It's again that it's although like there are two dependencies here, right? But I have to start solving the 3 first, right? So when I want to solve the 3, I want to solve second and then the first, right? So now after I recurse, right? Just see that what happens if I solve the first one. The first one, like if I have the opt first, OPT first, right? So basically that's unsurprisingly, it's really probably it's just a W1. I just keep up, like just use the first node, right? And after I solve this one, right, so basically the only thing I do is that I update my M1 equals to make it to equal to be optimum first, right? So, and basically, so that just says that now I sort of have an idea. I know what is opt1. Like next time you ask me opt1, I'm going to give you W1, right? So this is still a bit silly, right? So because right when you are solving the opt1, of course you only have one job. You don't need to do much in order to figure out the optimum solution, right? But when you start to look into the opt2, it start to become a bit interesting, right? So when you want to solve the problem, right, you only have 2 jobs, whether you want the first one or the second one, right? A bit of intelligence is going to happen here, right? So sometimes if you realize that the value of the first job is so large, then you don't execute the second job. But on the other hand, if the value of the second job is too large, then you don't execute the first job, right? So somehow you just make a decision here by looking at the concrete number here. Say that opt2 is you just decided to do something, and then at the end your opt2, you sort of figure that it's a concrete number, right? So I'm just making this up, right? It's 20, right? So originally when you just run this recursive, right, so without any memorization, you just forgot this 20, right? Just return the 20 as part of the solution of the opt3, and the 20 is really just floating around. It's you never sort of remember you ever compute opt2, and you never sort of remember the opt2 equal to 20. You sort of like it's almost like you're a bad student. You did a lot of exercises in the textbook, but you never remember anything, right? The only difference here is that, right, after you compute the opt2 equal to 20, you write that back to the m, right? So m2 becomes 20, right? In this case, right? So now you have opt2, you have the solution for 2 and 1 ready, then you sort of know how to tackle 3, right? So basically based on looking at these 2 numbers, you sort of have another decision for the opt3, right? So let's say this is 35, right? I don't know, I'm just making some sort of number as up, right? So and then you sort of solve this particular problem, right? So now things start to look interesting, right? So your opt4 basically it's a function, right? It's a function, right? The max of opt2, opt3, and the opt2 plus W4, right? This is how you compute opt4, right? So now you sort of know that opt3 is sort of returned from here, right? So say that it's a 35, you get this number. Now you sort of want to move to opt2, right? So originally you want to expand this opt2 again, I do the recursive again. But now before you compute, before you start to do the recursive call, right? Before you sort of look into the solutions here, you sort of see, well, it seems that I have computed this the opt2 because m2 is not empty, right? That's a sign that I computed the opt2 before, right? So instead of like expanding this tree, I just say that I look into this table and say that opt2 is really just 20, right? I don't even need to do any computation here. Right, that's the reason that I sort of save the computation at this end, right? So let me just erase a little bit here, and let's see what's going to happen when I'm doing the fifth one. The fifth one has the same similar problem, right? So after I give you the opt3, like let's say this is the 50, right? So I tell you this is 50. Now I need to move to solve the opt3, right? But before I even try to recursively solve the opt3 again, I sort of look into my array and realized that, whoa, this is not empty. I can directly use the 35 to replace that, right? I have computed again. I know the solution is 35, right? So none of this tree is not, none of anything, like none of the nodes that are on the right-hand side of this recursive tree needs to be expanded. No need any computation at all. Right? That's the reason that we sort of managed to delete a lot of computation here, right? So there are computation here, right? A lot of computation here. So eventually we have a very, very narrow search path, and this gives us the polynomial time algorithm. Right? That's the whole high-level idea, right? You just have a cache, and before you run any recursive call, you look into the cache and sort of see that whether I have computed this before. If I have done so, then I just don't recurse. If not, then I recur. Right, so now let's just switch back to the slides over here, right? So these are really just the pseudocodes for our algorithms, right? So it's called top-down because as we will see that there's another approach that makes things a little bit more efficient, right? So the whole code here is really just doing the housework, right? So you sort of need to compute all the pi, right? So still remember pi is the max j such that j is compatible with I, right? So you sort of have to do this, right? This has to be done in so basically it was very careful in defining in describing how you can get this done, like using the binary search, right? So at the end of the day, right, it's really just this is the DP component, right? So this is the DP, right? So basically you should imagine that there's an M array over here that's serving as the cache, right? So when you want to compute the optimum of J, right, before you even try to do the recursive, you just check whether the j is ever exists here, right? So if j like this is never computed, you just go ahead and do the recurse, but otherwise you directly return the value over there, right? So let's see what was that. So this was the pseudocode for the original. Let me just paste that and see whether I really like this whole functionality of copy and paste, copy. And let me just paste that and do a bit of comparison here, right? Paste image, right? So it's a bit smaller, right? So let's hope that like you can still read that, right? So the only difference here, right? So let's just compare this component, this function, and this function over here. The only difference here, right? So there's a base case, right? This sort of ignored the base case, but in case you don't look into the base case, right? The only intelligent thing we are looking into is that if m is initialized, right? I just do a checking of m, right? If m is initialized, I'm not going to do the recursive call at all. I'm going to directly recall whatever that's over there, right? If it's 30, then return 30, right? But compared to the original algorithm, just no matter what, I'm going to do the recursive call, right? So just this, by being a little bit smarter, and all of a sudden we are able to push the running time substantially down, right? So this is the exponential running time, and this is actually the polynomial running time. And why this is exponential running time? Actually, if you look back to the recursive tree that's down here, right? So So basically, if you just keep constructing this kind of example, right? So you can sort of see that your running time is equal to Tn minus 1 plus Tn minus 2 and plus, right, when you do comparison it's over 1, right? So this is the running time for the example, that's the instance over here, right? So this is actually the worst case running time, right? So let me just re-emphasize a bit, right? So the running time is highly sensitive to the layout or the structure of your input. Sometimes the running time can be polynomial, and sometimes it can be exponential, right? So but we care about the exponential running time, and that's the reason that we can like we can sort of look into this. This is one of the more harsh cases, right? So harsher cases, right? So if you look at you continue to construct a sequence, right? So you continue to pad this a lot of jobs, right? To make sure you have n jobs, and then you look into the running time. The running time here is actually expressed into this recursive form, and then it turns out that this is what people call the Fibonacci number, right? So and that's the reason that this is actually an exponential time algorithm, right? So this is an exponential time, and this is actually polynomial time, right? So you can sort of see that my recursive call is not going to be lot larger than the size of the array m here. Let's see whether and size an array here, right? So which also really just means that like by having a little bit of a trick of caching, that we do gain substantial performance